Today's topic is AC source transformation and nodal analysis. And by now it's a familiar topic. In DC circuits, we can replace a voltage source in series with a resistor and replace that with a current source with a resistor in parallel. And we have a surefire method to solve for any voltage or any current in any circuit by following the steps in the nodal analysis process that yields a system of equations that simultaneously solves all the node voltages. And here's the good news. The same physical laws that govern voltages and currents in a DC circuit apply to AC circuits as well. Kirchhoff's current law, Kirchhoff's voltage law, Ohm's law, law of conservation of energy. So practically speaking, what this means is that if we transform our AC circuit sources into phasors and our resistors, inductors, and capacitors into impedances, then all our tricks to solve circuits will apply. For example, suppose I have in the phasor domain a voltage source with an impedance in series. Then in the same way as a DC circuit, I can transform that into a current source with an impedance in parallel. So for example, suppose I have a voltage source V is equal to 82 volts with an angle of 70 degrees. Okay, that's the 82 is the RMS value of the time domain amplitude of that sinusoid. Notice here that it's again a sinusoid showing that it's an AC source. And it's also in series with this impedance. And that impedance I'll call Z. And Z is equal to, well, it's equal to the real part or the resistor. And I see that it's in series with a capacitor. And a capacitor is a negative impedance and a reactance, and the value is 40. So the total impedance is 9 minus J, 40 ohms. And I see that that is a voltage source in series with an impedance. So I can convert that into a current source. Now notice that the arrow is pointing down because my polarity of my original voltage source is minus to plus from top to bottom, so the arrow is going down. And I'll label that I. Notice I put the hat or the arrow on top of there indicating that it's a phasor or a complex number. It has magnitude and it has a phase. Then I'm going to reconnect it to that impedance in parallel, and I'll call that Z, where I is equal to V over Z, which is equal to 2 with an angle of 147.3 degrees amps. And that's my source transformation. Now notice here that it wasn't connected to some kind of circuit, so I just kind of leave that blank. But let's do a problem where I actually have a part of that circuit where I'm going to leave the same. So here's my circuit. I'll call this my circuit. That's the rest of it. But I see here between nodes A and node B that I have a current source with an impedance in parallel. Okay, so what I can see here is I'll label things. I like to label things before I do any problems. I'll label this one Z1, I'll label this one Z2, and I'll label this one Z3, and I'll identify them below. Not I1. Let's say that I is equal to 4 with an angle of 0 amps. I see that Z1 is equal to, well, that's purely inductive, so that's a 0 real part. It's plus because it's an inductor, J, 2 ohms. Z2 is equal to, well, that's a 5 ohm resistor. That's purely resistive or real, so that's the 5 plus J, 0. There's no imaginary part or no reactance. That is ohms. And Z3 is equal to another real resistor. That's the 3 ohm resistor, so I'll call that 3 plus J 0 ohms. So I've defined all the elements in my circuit, and I see that my solution or what I want to find is the voltage VR across the 3 ohm resistor, or the impedance Z3. So I notice that I have a source transformation, and I'm going to go ahead and redraw that as a voltage source, minus to plus from bottom to top, because the arrow is pointing up. And here's my voltage V, and I'm going to place in series in that circuit my impedance Z1. And notice that I'm going to put my two nodes here, A and B, just to indicate that that's my source transformation, and I'm going to redraw the rest of the circuit as shown. So here's my impedance Z2, and here's my impedance Z3. And I'm going to redraw where my voltage that I want to find in my new circuit. Now I can see clearly that I have a voltage source. By the way, that voltage source is equal to I by this source transformation times Z1, which is equal to 4 with an angle of 0 times J2, which is equal to 8 with an angle of 90 degrees volts. So that's V. But now I see that I have 3 impedances in series, and I want to find the voltage across one of them, Z3. So I can use voltage divider rule to find it. So VR in my final answer is going to be equal to the ratio of my impedance Z3 divided by the total impedance in that path, which is Z1 plus Z2 plus Z3. Notice that I put arrows on top of all of those impedances there. And I'm going to multiply that by V, my total voltage. When I do all that math, I see that I get 2.91 with an angle of 76 degrees volts. And that's my answer. That's the voltage drop across my impedance, or my 3 ohm resistor. Okay. Now, again, the same physical laws that govern voltages and currents in an electrical circuit apply to AC circuits as well. So this also applies to nodal analysis, where the steps in the process is exactly the same. So I'm going to use this problem here, and I'm just going to walk through the process how I would solve an AC circuit using nodal analysis. So I just redrew that circuit, and the first thing that I'm going to do is I'm going to label everything. So here's V1 and here's V2. Here are my voltage sources. The next thing I'm going to do is notice where the elements are in my circuit, and I see 3 more. I have Z1 right here, I have Z2 here, and I have Z3 right there. So I'm going to label everything and just clean up all the known quantities in my circuit to start off with. So here I have V1, which is equal to 10 with an angle of 30 degrees volts. V2 is equal to 7 with an angle of 20 degrees volts. And then I have 3 impedances, Z1, which is equal to, I can see that Z1 has a real part, which is 6 ohms, that's the resistor, plus an impedance, a reactance, which is positive because it's an inductor, so that's plus J, 8 ohms. Z2. Well, Z2 looks like it's just purely capacitive, so there's 0 real part, and the reactance is minus J, 20 ohms, as shown. Z3 is also purely resistive, and that is a 12 ohm resistor, so it's 12 plus J, 0 ohms. And I have all my elements now identified, and I'm ready to go ahead and start the process. So the first step is to label nodes and identify one of those nodes as ground. So the first thing I want to do is figure out just how many nodes I have. Well, I could see that I have one here, here's A. I have one here, that's B, in between those three impedances, and I have one here. We'll call that, or label that C. And the fourth node is collected down at the bottom. I'm going to call that one ground. So I'm done with step one. Step two is to assign the voltages, and I want to note which ones are known and unknown. So I'm going to start off to the left here. I'll say that VA is equal to V1. Well, I know what that is. I know what V1 is, so that's known. I have VB. Notice again that these are phasors, so I have an arrow on top indicating that it's a vector with magnitude and phase. VB is unknown at the start of the problem. VC is also is known to be, I'll call it V2 right here. V2. And if I want to be complete, I had 4 nodes, I have 4 voltages at those nodes, and V ground is simply going to be equal to 0, and that's just by definition. This is my voltage source or the voltage that I reference at 0. This is my defined ground. So I'm done with step 2. Step 3 is to label the currents. Okay, so I'm going to go ahead and do that. I'll call this current here capital I1. I'll call this current here capital I2. And I'll call this current here capital I3. Could I have put those currents in the opposite direction as I label them? Yes. And if you follow the steps exactly, then the process will, or the math will take care of itself. And if I have a negative value, well, it just means that my arrow is pointing in the opposite direction. So that's not a problem. So I've labeled those currents I1, I2, and I3, and I want to define what they are in terms of node voltages, and that's my application to Ohm's law here. So I'll say that I1 is equal to, where'd it go? I1 is equal to, well, it's going from VA to VB divided by Z1. And I2 is equal to the voltage at B, so it's going from the node B to the ground, so that's minus 0 divided by Z2. And I3 is equal to going from node B to node C, so that's VB minus VC, divided by the impedance in between, which is defined as Z3. So I've labeled my currents now, and I'm done with step 3. Step 4 is to apply Kirchhoff's current law, KCL. And I'm going to see that I want to apply it at the node with the unknown voltage. And that's this one right here, VB. So I'm going to say that I'm going to apply KCL at node B. All right, node B. All right, so what I have is a current going in, I1, and that's going to be positive. I also have a current going out, that's I2, that's negative, and another current going out, that's I3, and that's also negative, and I set that equal to 0. So there's my KCL. Done with step 4. Step 5 is to substitute and solve, or plug and chug. So I'm going to substitute the values in step 3 with step 4. So I1 is equal to VA minus VB divided by Z1. And I'm going to subtract I2, and I2 is just VB over Z2. And I'm also going to subtract I3, which is VB minus VC. I'm going to put parentheses around that just to show you. Okay, notice here I'm very meticulous about the arrows, indicating that they're all phasors, and the impedance is Z3 here, just plugging it in to step in those between those two steps 3 and 4, and I set that equal to 0. Now, if I combine like terms and regroup things, I could see that I have minus 1 over Z1 times VA plus 1 over Z1 plus 1 over Z2 plus 1 over Z3, this is just algebra, times VB, which is equal to 1 over Z3 times V sub C. Now, what are the known things that we have here? Well, VA is known. VA is V1, and VC is also known. VA or VC is V2. That's what we've defined in the original problem. So the only thing that I don't know here, again, is my voltage at node B. So I'm just going to solve for VB and collect the terms and put it on the other side of the equation. I can see that VB is going to be equal to 1 over Z3 times VC plus 1 over Z1 times VA divided by 1 over Z1 plus 1 over Z2 plus 1 over Z3. When I do the math, I could see that VB then is equal to 10.1 with an angle of 4.32 degrees volts. That's my answer. That's the voltage at node B. Now, done with step 5. Now, suppose I wanted to check my answer. Is there another method that I could use to solve to find for the voltage at node B? Well, let's take a look at it and clean it up a little bit and check my answer here. Okay. So it's possible that what I can do is take a look at this very same problem and look at it as a source transformation problem. And I've done that before the lecture here just to kind of move through the process. And I can see that I have two voltage sources with impedances in series on the left side and on the right side, and the circuit in the cloud shown here is the circuit that I'm going to leave the same. So notice here that my circuit is just simply that impedance Z2, and in each side, or on each side, I've transformed my voltage source with an impedance in series with a current source and an impedance in parallel. Okay, and I've gone ahead and calculated what I1 would equal. That's V1 over Z. So this is my current I1 in that source transformation, and my current I2 is shown here. Well, now I have two current sources with three impedances in parallel. Everything is in parallel, so I can add them together. So here's what I'm going to do. I'm going to take my impedance I and call it an I prime here, and I prime is equal to the sum of I1 plus I2. And so when I do that, I get this value here, 1.48, with an angle of minus 7.5 degrees. And that's my current. The other thing that I could do is I could combine the three impedances now that are in parallel, and it's the same potential across it, and that potential is the same potential as VB in my original problem. And here's my node VB right there. So when I combine the three impedances, I get 6.83 with an angle of 11.8 degrees. And now I can solve for the voltage across by simply multiplying I times the impedance, which is equal to, here, let me write that in there, I times ZT, here we go, which is equal to 10.1 with an angle of 4.32 degrees, which is the same answer as using nodal analysis on that same circuit. So they match. I'm using two different methods to solve it. We've gone through an example for nodal analysis and verified it using source transformations.